Bonjour à tous, welcome everyone. Tout d'abord, merci à toutes d'être présents pour cette nouvelle édition des conférences Nirenberg géométrique. Tout à fait, en anglais. So first, we'll have an executive about the lectures today. It's a fine day. They are probably going to be online, and unfortunately, it's not yet right. I'll be able to come for some absolutely incredible reason. But the conferences will be online, and we will have the conference online in this room. And also we welcome you to come. There will be the wine and cheese reception as planned on Friday. Due to the presentation of our prestigious speaker today. So Joshua Zahl is an eminent professor from Nankai University's Chairman's Institute of Mathematics. He received his PhD from the University of California at Los Angeles in 2013. After holding an NSF postdoctoral position at the MIT, he spent 9 years in Canada at the University of British Columbia. He made significant contributions in several areas of analysis and geometry, and received several prizes, including the PIMS UBC Mathematical Sciences Early Career Award and the ICBS Frontiers of Sciences Awards in Mathematics. Recently, together with Hong Wang, he solved a more than a century-old Kakeya conjecture. Will be a speaker of the upcoming International Congress of Mathematicians in 2026, and we are very very lucky and honored to have him with us this week. Professor Zahl, I will now give you the floor. All right.
Thank you. Thank you for the invitation to come here. Pleasure to visit and to speak. So I'm going to talk today and the entire week as well about a recent result that she and I proved on the Kakeya set conjecture in 3 dimensions. Sort of the lurking in the background of what I want to discuss. And the overall plan is today I'm going to talk about the Kakeya set conjecture more generally and why this is an interesting question, one that people in harmonic analysis and geometric metric theory care about, even if you don't care about geometric metric theory per se. The next 2 talks, so one by myself and one by Hong Wang, we're going to talk about some aspects of argument. And so we, so 3 years ago now, proved a special case of the Kakeya set conjecture in 3 dimensions, called we call it the sticky Kakeya conjecture. And some of you might remember I actually came and gave a talk at the CRM on this topic a few years ago. So the talk will be somewhat similar in flavor to that one, although very much inspired by later developments. And then Hong will give a talk which explains how to go from the sticky Kakeya conjecture, that special case, the general theorem. A lot of new ideas are needed, but this sticky case plays an important role. And then Hong's final talk, the plan is to discuss more broadly where one goes from there, put the Kakeya conjecture in a broader framework of questions that we would like to answer. Okay, so to circle back, I'm not going to talk today about any details of our proof. That's reserved for tomorrow and Thursday. Instead, I want to give you a sense of what the Kakeya set conjecture is and why it's interesting. So it concerns objects called Besicovitch sets. Sometimes these are also called Kakeya sets. The 2 terms are synonymous. So I'll give you a definition. It's been wonderfully bored. I've forgotten. A Besicovitch set is a compact subset of Rn that contains a unit line segment pointing in every direction. So these sets don't have to be mysterious. A closed disk of radius 1/2 or larger is an example of a Besicovitch set. But rather surprisingly, in 1919, Besicovitch constructed an example of a Besicovitch set that has Lebesgue measure 0. He did this in the plane, but once you can do this in the plane, you can do it in higher dimensions just by taking a Cartesian product with an interval that gives you a measure 0 Besicovitch set in R3, so on and so forth. So I can say there exists a Besicovitch set. He didn't call them Besicovitch sets. So I'll say subset R2, but from there Rn with Lebesgue. Okay. Besicovich's original motivation for constructing these sets is not a question we're so interested in today. He was interested in some subtleties related to Riemann integration. If we have a function of two variables that's Riemann integrable in the sense that the upper and lower Riemann sums converge, then can you do some analog of Fubini's theorem, where you first try to Riemann integrate in every vertical slice and then Riemann integrate that, say, integrate in y for every vertical slice and then integrate in x. And if you ask, can you integrate in y for every slice, then that can be a bit subtle, right? Because if you have a function that's Riemann integrable in two variables, that doesn't mean that every vertical slice is integrable in one variable. And Besicovitch asked, well, what if you tilt your coordinate axes a bit? Then maybe this function becomes Riemann integrable for every vertical slice, right? You can imagine a function which is, let's say, one on the rationals, 0 on the irrationals of a single vertical line. That's a counterexample to the hope that your function is Riemann integrable for every vertical slice. But if you tilt your head sideways, you fix that problem. And Besicovitch was wondering, if you have a function of two variables, which is Riemann integrable as a function of two variables, and you always rotate the coordinate axes in such a way that you can do Fubini. And it turns out the answer is no. That's a little bit subtle, but the existence of a measure 0 Besicovitch set can be used to construct a counterexample. So this was Besicovich's original motivation. These days, this is not the reason we're interested in these sets. I just mentioned that as a historical aside. What does it mean to have a compact set which has the data metric 0? Well, if I let k sub delta denote the delta neighborhood of my set, then if you're compact and you have measure 0, then the volume of this goes to 0 as delta goes to 0. And as a consequence, I can extract the following object. So I'll write it as a statement and mention briefly why this is true. So as a corollary of the statement that these objects exist, it's that for every positive number eta, there exists some positive delta, and a set, I'll write this as blackboard bold T, of rectangles of length 1 and thickness delta, pointing in delta separated directions. Here I say the direction of a rectangle is the direction of its major axis. And a set of rectangles pointing in delta separated directions. Say for every pair of rectangles in the set, their corresponding directions, like angle at least to delta. So pointing in delta separated directions with, well, I want there to be a lot of these rectangles. If I add up their volumes, each one of these has volume delta. And I want there to be about 1 over delta of them, just roughly a maximal number. They come delta separated directions. So I want this to be at least 1. But the volume of their union is very small. That's the same eta that I had here. Right. So what this is saying is for every positive eta, there exists some delta, which is going to be quite small, depending on eta, so that I can find these rectangles pointing in delta separated directions, so that the sum of their areas is roughly 1, bounded below by 1 at least, but the volume of their union is arbitrarily small. And how do I find such a collection? Well, you give me your favorite eta. I choose delta sufficiently small so that the volume of this set is less than eta. My set K contains a unit line segment pointing in every direction. Its delta neighborhood contains the delta neighborhood of a unit line segment pointing in every direction. It's more or less a rectangle of length 1 and thickness delta. The distinction is important. And from that, I can extract a finite set of such lines pointing in delta separated directions, roughly 1 over delta of them. And this gives me my family of rectangles. So this point from here to here is not 50. Now, we might call this the Besicovitch compression phenomena. And it turns out that this is a interesting and somewhat fundamental aspect of Euclidean space in dimensions 2 and higher. And it has consequences in Fourier analysis. So that connection wasn't discovered until the late 1960s, early 1970s. And so to talk about that, let's recall the Fourier transform. So if I have a function f from Rn to C, I'm going to define its Fourier transform. F hat of C is the integral f of x e to the negative 2 pi I x dot c dx. And similarly, if I have the function g from Rn to C, I'm going to define the inverse Fourier transform of g, be the integral d of c e to the 2 pi I x dot c dc. And at least formally, if you compute these integrals, if you have a function f and take its Fourier transform and then take its inverse Fourier transform, you recover a function f. If your function f is sufficiently nice, maybe it's Schwartz or smooth, compactly supported, something like this, then all of the integrals that I've written here converge without much difficulty, and this is a true statement in a pointwise sense. But more generally, if your function f is rougher, you can ask, in what sense can I make sense? Can I interpret an inequality like this? We can say, in what sense does this hold? If your function f is in L2, then you no doubt know that its Fourier transform is again in L2. In fact, the L2 norm is preserved, and the inverse Fourier transform will again be in L2. In an L2 sense, if your function is in L2, this makes sense as an equality of L2 functions. What if your function is in LP for some value of p not equal to 2? Well, if it's in LP for p bigger than 2, already it's very hard to make sense of this integral. So it's not, Fourier transform is not bounded as map from LP to any reasonable function space. If your Fourier transform is in LP first, if your function f is in LP for some p less than 2, then the Fourier transform makes sense, but you get something in p LP prime, and now the inverse Fourier transform doesn't make sense. So it's rather fraught trying to interpret this equality here. Now you might ask, why do we care about starting with the function and taking its Fourier transform, undoing it? This seems like a complicated way of just getting back where you started with. But one of the reasons we care about the Fourier transform, one of many, is that it intertwines differentiation and multiplication. Right? You have one way of differentiating a sufficiently nice function is you have a function, you take its Fourier transform. Let's say I have one variable, you multiply it by 2 pi I c, you undo the Fourier transform. This gives you back the derivative of your function. And this can be a useful way to define differentiation and more general differential operators in a setting where your functions are too rough, for example, for differentiation to hold in classical sense, right? This is the launching off point for many modern studies in PDE. And so there's a broad class of linear operators which are of the form, start with a function, take its Fourier transform, do something, undo the Fourier transform. It's an extremely broad class of operators. And the simplest possible thing you could do is start with a function, take its Fourier transform, do nothing, undo the Fourier transform. And you'd better understand that extremely well before there's any hope of understanding any of these more complicated operators. And even that extremely simple thing is somewhat fraught because we need to think carefully how to make sense of the convergence of these integrals. Okay, so there's various solutions, attempts at solutions to tackle this kind of question. Let's start in one principle, where we can work over R. And what I could do is I could define T sub R of F And what I'm going to do is I'm going to take the Fourier transform of f of c e to the 2 pi I x dot c dc. But I'm just going to integrate from negative r to positive r. I'm truncating this integral. And we could then ask, is it true? And indeed the answer is yes, that T sub r of f converges to f in LP for all p between 1 and infinity. So what I mean by this is there's a few different interpretations, but fix your favorite value of p between 1 and infinity. And consider this operator T sub r of f. You could start by restricting say Schwartz function, so this certainly makes sense. And this is an operator from well, if you begin with a Schwartz function, you're going to get back out something which is in LP, and this converges to get in LP. Thus, it extends to a bounded function from LP to itself, and indeed it converges to get in LP. So there's nothing complicated going on here, right? We have these partial or these truncated Fourier integrals, and the fact that T sub r of f converges to f in LP is more or less equivalent to if I were to just integrate from -1 to 1. This defines the bounded operator from LP to itself for all p between 1 and infinity. The boundedness of this, just the boundedness of the order. So this is very classical. What about in higher dimensions? So we could go to R2, for example. Is there an eraser? Calculator? No, is there? So there's a few things you could do in R2. So what's going on here, right? The point is that as r goes to infinity, we are exhausting the real numbers in some reasonable way. And you could ask, what's a reasonable exhaustion of R2? And there's many possibilities. But one, we could define maybe S sub r of f. So here S is for the square. And I'm going to evaluate this, I'm supposed to evaluate this in x. This is the integral over the square from -r to r squared. Same thing, f hat of c e to the 2 pi I x dot c dc. And another thing you could instead consider doing is maybe I'll write this as b sub r f of x. I'm going to integrate over the ball, center of the radius r of f hat of c e to the 2 pi I x dot c dc. And we could ask the same question in both of these cases. If you start with a LP function, is it true that S sub r of f converges to f in LP? Is it true that B sub r of f converges to f in LP? As r goes to infinity for p things. Question makes sense. Looks vaguely plausible. The answer might be yes. And at a minimum, here you have these are both exhaustions of R2 by increasingly big sets. In this case of the square, the answer is yes, and it's more or less just the one-dimensional theory. So S sub r of f converges to f in LP for all p between 1 and infinity. What happened for B sub r? Well, already we knew it was not going to be the case that B sub r of f converges to f in LP for all p between 1 and infinity. That's too much to ask for. The boundedness of this is equivalent to the boundedness of B sub 1. So we can ask, is it true, or for which p? Is it true that B sub r of f converges to f in LP? And this is the same as saying that B sub 1, so this is the function where you're just integrating over the unit ball as an operator from LP to LP is bounded, right, as finite operator. And so if you plug in a fairly straightforward test function, like let's say the characteristic function of the unit ball, you can compute what's going on here. Right, what is this doing? When r is 1, you have a function, you take its Fourier transform, you multiply by the characteristic function of the unit ball, you undo the Fourier transform. Right, multiplying by the characteristic function of the unit ball and integrating over all the space is the same as just integrating the inverse Fourier transform over the unit ball. Then you plug in a simple test function and just say the characteristic function of a unit ball. You can compute what's going on. You get something involving Bessel function that has a certain rate of decay. And And that rate of decay is sufficient to be an LP for certain values of P and not for others. So there was a conjectured range of P between 4/3 and 4, where it was thought that this was going to be a bounded operator. It's certainly a bounded operator from L2 to L2, right? Because you have a function, you take its Fourier, an L2 function, you take its Fourier transform, you haven't changed the L2 norm. You multiply it by the characteristic function of the unit ball, you just chopped it to 0 at certain places. You have not increased the L2 norm, that's for sure. You undo the Fourier transform again, you haven't increased the L2. So this is certainly bounded as a function from L2 to L2. Means this guy converges to F in L2, there's nothing surprising there. It was thought that there should be some open range of P for which you have convergence, and this rather surprising discovery of Charles Kaufman in 1970, well, I'm not exactly sure what year he discovered it, but I think it was published in 1971, is that this is not true. This is bounded as an operator from L2 to L2, as we knew, and the corresponding convergence is true when P is 2, but it's false for every other value of P. So Kaufman came up with a counterexample. That's his proof is a counterexample, and unsurprisingly, given my lead-up, his counterexample comes from the existence of a measured zero Besicovitch set, and more concretely, from this Besicovitch compression problem. So I want to spend a few minutes describing how Charles Kaufman's counterexample worked. And the conclusion, a broad conclusion of the counterexample, is even if you don't think you care about geometric measure theory, Besicovitch sets, things like this, if you care about the Fourier transform, if you care about the boundedness of operators arising defined using the Fourier transform, which underlie our modern definition of differentiation, etc., then this Besicovitch compression phenomena is simply a feature of Euclidean space that has to be taken into account when studying these things. So you're forced to care about it whether you like it or not. You care about this much broader pattern. So ultimately, this is why people care about the Kakeya conjecture. I'll get there in a few minutes. It's not because of its inherent interest here. It's that's Kaufman forced us to care. Okay, so I'm going to keep this forward. So I won't have time to give you the entirety of Kaufman's proof, but I want to give you some flavor of what it says. So let's just make sure we understand what we're trying to do. We're trying to prove, so maybe I'll just write down the statement, the theorem. And now I'm blanking if the paper is 1970 or 1971, but I think it's 1971. I'll check that before quoting me. It is that this operator, E sub 1, as an operator from LP to LP, this is unbounded for all P not equal to 2. So to get a sense of why this is true, let's take your favorite value of P. Let's take a value of P bigger than 2. P less than 2 works by equality. And what does it mean to show that this operator is unbounded? Well, you give me your favorite large number C. I want to show that this function, this operator has operator norm larger than C. Right? So I need to find a function so that when you apply this operator to that function, you've blown up the operator norm by more than C. You can do this for every C, you're unbounded. Great. How are we going to do it? Well, you give me your favorite big number C. I'm going to pick an eta, just something like the reciprocal of C. It's also related value of P. Maybe it's something like the reciprocal of C. And then this corollary means there exists some very small delta. So I get this amount of Besicovitch. Okay. So let's keep that in the background. And so this is
why is it called compression? Like, what are you compressing here?
Yeah. I'm compressing these long, thin rectangles into a very small region of space. Yeah. They want to be disjoint from each other because they point in different directions, but there is some amount of compression happening. Great. Okay, then I'm going to come back to that compression statement in a moment. So maybe one thing I'll say some classical statement. So let's say if B1 of F, or okay, I'll say if this operator had operator norm less than C, then some, let's say, classical Eli Stein, perhaps even predating Eli Stein, style harmonic analysis would tell us the following consequence. So we can say, let's take any finite set of unit vectors we want, let's say V1 through Vn, everything's in the plane, the unit vectors. And maybe as a spoiler alert, you could ask, what makes this square so different from the ball? That one of these is bounded for every value of p between 1 and infinity, and the other is not. And it's that the unit ball has a lot of normal directions, in fact, in every normal direction, whereas the square only has 2 or 4, depending on how you do your counting. Right? And so that's the critical thing, is you have so many normal directions, and all those normal directions are used to achieve the Besicovitch compression. So let V1 through Bn be unit vectors, everything's in the plane. I'm going to choose them. I'm going to choose n to be the reciprocal of delta, and I'm going to choose these to be pointing in delta separated directions, but for what I'm about to say, I don't really need that yet. And I'm going to let H1 through Hn be the associated Hilbert transforms. So I'll draw a picture of what that means. I'll say B, the associated Hilbert transforms. So what do I mean by this? I'm being a bit too vague, but let's say V1 is a unit vector pointing in some particular direction. Well, I'm going to take the half space, or in this case, the half plane, passing through the origin, which has normal direction VI. So this is a half space. And when I say the associated Hilbert transform, what I mean is this is a Fourier multiplier. What it does is you give me a function, I take its Fourier transform, I multiply it by the characteristic function of this half plane, or equivalently, chop it to 0 on the other side of this half plane, and then I undo the Fourier transform. And that operator is bounded in LP for every p between 1 and infinity with some certain operator norm. But now I have a whole bunch of these, all associated to different directions of unit. So let's say this is true, and let F1 through Fn be functions. These are from R2 to C. So then I have a certain vector value inequality, if you will. And so what I'm going to do is I'm going to apply the Hilbert transform associated to this vector pointing in direction VI to the function Fi. I'm going to square that. I'm going to sum, take a square root, and I'm going to take its LP norm. This is LP and R2. And this is going to be bounded by at most C times sum of the Fi squared to the 1/2 LP. So what I'm claiming is the unit ball. So this is a Fourier multiplier, right? You have a function, you take its Fourier transform, you multiply by the characteristic function of the unit ball, you undo that Fourier transform. The unit ball has a lot of normal directions. You give me your favorite unit vector. If I translate and rescale the unit ball, it begins to look an awful lot like a half plane with that particular unit vector, right? You can imagine that this is an extremely large unit ball, so large that really all you're seeing is this half, if appropriately scaled. And so here's a step I'm not explaining how to do, maybe you can believe. If this operator is bounded, all these different normal directions, then it gives us a type of vector value inequality as well. Why is this useful? Well, I'm going to come up with a counterexample to this statement here. So how do I do that? I need to come up with a set of vectors, v1 through vn, and a set of functions, f1 through fn, so that an inequality like this fails. What are my vectors? They're just going to be a set of vectors pointing in delta-separated directions for more or less every delta-separated direction. And what are my functions, f1 through fn? They're going to be the characteristic functions of rectangles of length 1 and thickness delta, which are very, very closely related to the rectangle coming from this Besicovitch formula. So let me tell you exactly what to do. We all remember the definition of the Fourier transform. I'm going to perhaps redraw first piece of this picture. So I'm drawing a set of long, thin rectangles pointing in delta-separated directions. The volume of whose union is extremely small. It's at most eta. Right here, eta is a small number, which is something like the reciprocal of C. My goal is to show operator below at least C. And I'm going to call this set of delta rectangles flat orbital T. And then I'm going to translate each one of these rectangles by distance, let's say 2, in the direction they're pointing. The idea is that after you do that, these rectangles are mostly disjoint from each other. There might be a small amount of overlap, but morally there's no overlap whatsoever. And I'm going to call this set T tilde. And I'm going to let Fi, maybe I'll even write this as T tilde. This is T1 tilde all the way through Tn tilde. I'm going to let Fi be, well, this is a slight lie, but let's just say we can pretend it's the characteristic function of T sub I tilde. This is a slight white lie. And let's figure out what's going on here. So what is the sum of the characteristic function of the sum of these Fi squared? That's the sum of the characteristic functions squared. Well, squaring characteristic function doesn't do anything interesting. This guy here, when you take an LP norm, is just roughly 1. It's the sum of characteristic functions of disjoint sets, the sum of whose masses is roughly 1. Raise that to any power you want. The right-hand side remains roughly 1. What happens when you apply HI to Fi? Morally speaking, what it does is it shifts this function downwards. That's not quite true. I'll talk about what it truly does. But let's just imagine for a moment that it shifted this function downwards. So what you get is that Ti, or the characteristic function of Ti, is roughly Hi times the characteristic function of Ti tilde. Let's imagine for just a moment that was a true statement. What this then tells you is this guy here looks like the sum of the characteristic functions of these shifted cubes. You haven't changed the mass, right? If you sum up the areas of all of these shifted cubes, you still get roughly 1. But circling back to this Besicovitch compression, the volume of their union is very small. What this means is the cubes are stacking up a lot. What this means is if you maybe write this guy here a little more explicitly, right? This is the integral of the sum of the HI squared. I'm integrating this to the power of P over 2. And then I'm taking a 1 over P. Just a 1 over P on the other side is not very important. If I have a bunch of characteristic functions of sets, and you add up their areas and it's 1, the volume of their union is very small, they're stacking up a lot. The moment you raise this to a positive power, this is blowing up. Right, so that's what's going on here. Or sorry, a power bigger than 1, but critical to this is blowing up. So this Besicovitch compression phenomena is underlying the unboundedness of this operator. Okay. Now I said it's a slight lie that applying the Hilbert transform shifts it. In reality, it smears it out, but it smears this function out in a way where there's a lot of stack up in this promise. Okay, so that's more or less the entirety of Charles Beckman's proof. And what it tells us is this Besicovitch compression phenomena can be used to give counterexamples to the previously conjectured boundedness of some operators that on the face of it have nothing to do with Besicovitch sets, anything like that. And a question we can then ask is just how bad is this counterexample? There's a few different ways of phrasing it, right? If I want to get blow up by at least some amount C, my F need to be quite thin. In order to see them, I need to be operating in a fairly high resolution. So one question you could ask is if I limit my functions F, be at resolution at most delta, how much blow up can I get? With some sort of quantitative statement about how much Besicovitch compression is possible. And this is what the Kakeya set conjecture says. It says Besicovitch compression can occur, this is what Besicovitch discovered, but only a logarithmic amount in the scale. So I'm going to write down what the Kakeya set conjecture says in its conventional form, which doesn't exactly conform to what I just said. Then we'll get a sense of what it really means. So this is the Kakeya set conjecture. Actually, quick question. Should I speak for 50 or 60 minutes? 60. Okay. Whatever. Kakeya set conjecture. So the actual statement is every Besicovitch set in Rn has Minkowski and Hausdorff dimension n. Now, of course, if you have Hausdorff dimension n, that implies you have Minkowski dimension n in Rn. So the conjecture is hedging its bets a little bit. Hausdorff dimension n. But what it perhaps really says, and one way of interpreting it, that's a very clean statement. A somewhat vaguer statement is Besicovitch compression exists but only a subpolynomial amount. Oh, maybe I'll say only a logarithmic. And I'll tell you what I mean by logarithmic in just a moment. So I've put this is already a heuristic statement. Logarithmic in quotes within quotes, so that should be taken not entirely literally, but I want to give you a sense of what it means. So I'm going to tell you one concrete conjecture, which is a version of the Kakeya conjecture. You can call it a discretized version of the Kakeya conjecture. So this is we're still on the heading of the Kakeya conjecture. And I'll say let delta be a positive number. Let T be a set of, so in the plane I was talking about rectangles of length 1 and thickness delta. In higher dimension, if you want, you can more or less think of that as the delta neighborhood of a line segment. That is, the two sets are more or less comparable. In higher dimensions, I could think of the delta neighborhood of a line segment. That makes sense. And I'm going to call that a delta tube. Be a set of delta tubes in Rn. So I'll just draw a picture. A delta tube is either the delta neighborhood of a unit line segment, or you take a unit line segment and you thicken it by delta just in the orthogonal directions. Whether you have the little caps at the end is not important. Delta tubes in Rn pointing in delta separated directions. So then, what I'd like to do is I'd like to relate the volume of the union of these tubes to the sum of the volumes of these tubes. And so on the one hand, I have the volume of the union. Of course, the volume of the union is bounded above by the sum of the volume. That's not in anything direction. I want some sort of bound times the sum of the volumes. And you can conjecture that maybe there exists some constant only depending on your dimension, making inequality with this true. But we already know that this is false because Besicovitch's construction shows that you cannot hope for an inequality of this form for any fixed constant. There's got to be some quantity which decays to 0 as delta grows, and you're asking what is that rate of decay? And so maybe I'll put in quotes. So as delta goes to 0, 1 over delta blows up. Log of 1 over delta blows up, but slowly, a subpolynomial way. And the reciprocal of that goes to 0, but slowly. So you might say log of 1 over delta reciprocal. I'll put that in quotes. So this is the idea. How does the volume of the union compare to the sum of the volumes? Well, you get Besicovitch compression, but only a logarithm. In R2, this was proved by Cordova. In sufficiently high dimensions, we have counterexamples to this, but you could raise this to some power depending on your dimension. Normally, we allow for a little bit more than logarithmic flow. So a statement we might say instead is there's a quantified statement, which I won't write for you in all of its entirety. But the idea is that for every epsilon, there exists some positive number C epsilon to make the inequality of this point true. So if you prove this in some concrete dimension, let's say epsilon and n, the log of 1 over delta is an example of a function which grows at this perspective. And this type of, so there's a quantified statement here, right? It's for every positive epsilon, and now in dimension n, there exists a constant c sub epsilon n, so that the following is true, let delta be positive, let t be set as delta, and this inequality. Hopefully that statement makes sense. This type of quantified statement we use so often, we even introduce a new notation for it. So we write greater than double squiggle to mean the left and the right hand sides are functions of delta, and they differ by most or the inequality holds up to a subpolynomial. So this is a discretized version of the Kakeya set conjecture. If you prove this, you prove that every Kakeya set has been in Rn has been costly dimension n. Converse is morally true, almost true. The Hausdorff mentioned version is very closely related, except instead of taking the union of the entirety of each tube, you take a fairly large subset of each. The distinction is not so important for us today. I'll pause for a moment. So any questions about what I've said so far? Okay, so just to recap, right? So Besicovitch constructed a Besicovitch set on measure 0. The Besicovitch or the Kakeya set conjecture is saying that so Besicovich's construction had roughly a logarithmic amount of compression with a scale that's involved, and that's the most you can do. There doesn't exist a better construction, or this is substantially better construction. The reason we cared in the past, the reason we first cared, is because the existence of these sets is closely related to some subtle behavior related to Fourier transform. And the reason we care now is similarly related. I'm going to talk about that a little bit at the end. Maybe it's time to tell you what Hong and I proved now that we have the language to do so. So, yes.
Is there an analogous statement conjecture related to Fefferman's result?
There is. So, okay. So one could ask, imagine, let's say in the plane, the Kakeya set conjecture were false. We know that this was proved by well, okay. I guess now we can quibble whether Davies or Cordova proved this statement here, but certainly Cordova proved something which implies this. Imagine if something were false, so an even more dramatic amount of Besicovitch compression were possible than sub-logarithmic. What would that tell us in setting time? Right, this is a good question. So Fefferman's Taylor example already tells us that this operator fails up. And what is this operator, right? So it is the function. What you do is you have a function f from R2 to C, and you take its Fourier transform, and you multiply it by the characteristic function of the unit ball, and then you undo the Fourier transform. That's what the operator is that we're interested in. And what is the characteristic function of the unit ball? It's radial. I'll draw its profile, very sharp. Right, that's the side view. And the general theme is when you're looking at Fourier multipliers, the rougher they are, the more badly behaved they are. And so, as an extreme example, if I were to place this by a smooth, compactly supported bond function, maybe something that looks like this, C infinity, then this is bounded in LP for every p between 1 and infinity. But you can imagine something immediate behavior. Maybe I have some sort of polynomial cutoff. So I'm 1, and then instead of dropping in a C infinity way, I can't really draw the distinction between C infinity and some polynomial cutoff, right? But you could imagine something like 1 minus the absolute value of x raised to some power c. What do I want to say? So when x is 0, this is 1, it drops, so the minimum of this and 0, hopefully I've written that properly. So what I'm trying to draw, I suppose I didn't draw that quite right, something which drops in a slightly smoother way than it's 0. And you could ask, is this bounded in LP, or for what range of P is this bounded? Right, so this is a slightly smoother version of the original operator. So there's a family of conjectures called the Bochner-Ries conjecture, which asks, how does the LP boundedness of that operator depend on this C here? There's a certain conjecture range. And in the plane, we know how to prove this in higher dimensions. And if you were to have a more dramatic counterexample to Besicovitch compression, or a more dramatic version of Besicovitch compression than what the Kakeya conjecture says is possible, you could apply a Fefferman-like argument and get a counterexample to the conjectured range of P for which this operator is bounded. But even when you start to smooth this thing out, the operator still blows up. So now there's more parameters floating around. There's how to see depend on P, et cetera, et cetera. But this gives you some sense.
Okay.
Yeah, great question. And that answered your question. Wonderful. Any other questions?
So here, it's true that always these operators, these APIs blow up, no matter what vector, so these operators blow up, in general, and what Fefferman proves is that if the whole thing was bounded, it would imply that this thing was bounded, which is not true.
Let's be careful. So, what is true in general is, let's say you have a strictly convex, let's say you have a convex set. If the corresponding Fourier multiplier for that convex set was bounded from LP to LP, then if you take any set of vectors corresponding to the normal vectors of that convex set, then this corresponding operator would be bounded, and you're allowed to choose whatever vectors you want from the normal vectors of that convex set. This would be bounded. Then what Fefferman did, that's a sort of general statement, is he said, okay, the convex set I'm going to choose is the unit ball. Ball's not that important, but lots of normal vectors is important. And then he constructed a concrete counterexample coming from Besicovitch. We know that the Fourier multiplier corresponding to the unit square is bounded. And this same thing would tell us, well, if the vectors I choose are all either the x direction or the y direction, then this guy is bounded. That's a true statement. But you're not going to be able to create a counterexample. You don't have a. Yeah, great question. Okay, so let me tell you what Hong and I proved, and then I'll tell you why people still care about the Kakeya conjecture today, even though Fefferman answered this question. So, I wrote down the Kakeya conjecture, both in its typical form that every Besicovitch set in Rn has Minkowski and Hausdorff dimension n, and then a discretized formulation, which is the version that in practice we like to work with. I'll say that the Kakeya conjecture was proved. For n equals 2, this was proved by Davies. Perhaps in this formulation, and then Cordova came up with a more quantitative proof of the statement more of this way. This was 1971. Cordova's work from the late 70s. And then in 3 dimensions, this is due to Hong Wang and myself from this year. And we proved something a little bit more general. I'll tell you what we proved. So it's the same sort of quantified statement. For every positive epsilon, there exists some constant c sub epsilon here, n equals 3. So that something is true. And what is it? Well, let T be a set of delta tubes in R3, which point in delta separated directions. That's fine. But actually, we work under slightly weaker hypotheses. So this is a theorem due to Wang and myself. So I'll say let T be a set of delta tubes in R3. That's a 3. And I'll say suppose that every convex set everything's inside the unit ball, if you want. I could say that, but Kakeya set or Besicovitch set is a compact subset of Rn containing a unit line segment in every direction. You lose nothing by assuming everything's taking place inside of the unit ball. I'll just mention that. Suppose that every convex set, I'll let W, contains at most the volume of W divided by delta squared of the tubes. Tubes from flat orbital T. There. So then the conclusion that we want is true.
Lose nothing if I do this?
Yeah, great. I'll answer that question as soon as I write the conclusion. So maybe what I should say So this is the same quantified statement you give me in epsilon that exists. You asked, why do I lose nothing? So maybe another way of what I should have said instead is the statement that Hong and I prove implies this formulation here. Phrased differently, if you give me a set of delta tubes in R3 pointing in delta separated directions, they satisfy this property here. Maybe up to a constant, maybe there's at most 100 times the volume of delta. That's not important. Why is it true that if you give me tubes pointing in delta separated directions, that they satisfy this property? So again, everything's taking place, let's say, inside of the unit wall. You give me a convex set in R3, it's up to a constant, it's more or less a rectangular prism, dimensions A times B times C. If the longest, let's say A is the longest dimension, then B times C. If the longest dimension is less than 1, it can't contain any tubes, so that's not very interesting. If the longest dimension is substantially longer than 1, well, I'm being inefficient because everything's inside the unit wall. So the longest dimension is roughly 1. What are the other two dimensions? B times C. The moment you have tubes, or unit line segments for that matter, contained inside of a rectangular prism of dimensions roughly 1 times B times C, that imposes constraints on the angles, on the directions they can point, right? As you try to increase the direction too much, it's going to leave the rectangular prism. So in the space of directions, if your line segment or your tube is inside of a rectangular prism of dimensions 1 times B times C, then on, let's say, the sphere, the parameter space of directions, you're in a little rectangular segment of dimensions B times C. And how many delta separated directions does that have? It's B times C over delta squared. So this is why the statement we've written here is a generalization of the hypothesis of the original Kakeya conjecture. Now, why write this hypothesis here instead of delta separated directions? There's two reasons. So first of all, what this is telling us is Besicovitch compression isn't an underlying feature of being direction separated. In fact, direction separated was a bit of a red herring. What this is saying is the way that convex sets can compress is if they are trapped inside of a larger convex set. Right? Take the delta neighborhood of a plane, you can pack an awful lot of tubes into that because a plane contains a two-parameter family of points. So convex sets are the only obstruction to convex sets, to tubes being almost disjoint. And you could replace tubes by, you have a family of convex sets, they don't concentrate inside of larger convex sets. This has forced them to be morally disjoint. This is a kind of covering theorem in the spirit of something like the Besicovitch or Bertelli covering theorem. You lose a little bit because the sets are extremely eccentric. It's quantifying how much you're losing. It's a function of the eccentricity of these convex sets. The other reason that this is a more useful statement is that the proof of this theorem, which I'll talk about a little bit next time that Paul will talk about, involves various types of rescalings and other types of transformations. And the property of pointing in different directions is not preserved under those rescalings. But this kind of statement here is, if you replace tubes by more general convex sets, then this kind of non-concentration condition is preserved under a much broader class of transformations. Okay, I hope the statement makes sense. This is what Hong and I, well, we personally a tiny bit more general, but this is something that Hong and I proved. And I want to spend, I guess we now only have 5 minutes, but the last 5 minutes discussing the modern interest in the Kakeya set conjecture. And this really started from a seminal paper of Jean Bourgain in 1991 concerning something called the Fourier restriction conjecture. But maybe an easier way to think about it is we want to solve this Schrödinger equation in, well, let's say 2 space and 1 time dimension. That corresponds to the Kakeya set conjecture in R3. What I'm going to say is true in higher dimensions as well. But let's talk about the Schrödinger equation. In 2 space plus 1 dimensions. And so maybe I'll write this as negative 2 pi I. So apologies to the mathematical physicists out there for the 2 pi I, but time derivative of u, I have a function u of xt, which is from R2 cross R to C, negative 2 pi I, the time derivative of u plus the spatial Laplacian of u is 0, and I have some initial condition u of x0 is u naught of x. Okay. And so the Schrodinger equation is a dispersive PDE, and one way to think about this is you begin with some initial distribution of your mass or probability, and as time passes, this is supposed to disperse. And one way of trying to make sense of that is we can take space-time averages. So I can integrate the solution in both space and time. And if my solution disperses, then what you might expect is that these space-time averages might be integrable for a certain range of p, which is a larger range of p than simply the initial data being integrable. Right? So if the solution is spreading out, you expect a higher value of p for the space-time average to be integrable. So maybe I'll say this precisely. So here's the question: for which p do we have an inequality for a bound of the form p of R3 less than or equal to some constant depending on p u of p of R2? This is a concrete question. And you can think of us. We begin with some initial data to the free Schrodinger equation. We solve the free Schrodinger equation for that data. That's a linear operator. So we're asking for which values of p is this operator bounded LP to LP. I'll say one other thing about how this relates to the Kakeya set conjecture. Hopefully the question makes sense. So first of all, let's observe, at least if your function is sufficiently well behaved, then satisfying the free Schrodinger equation, let's say I take a Fourier transform, my x variable becomes c in frequency space, and my time variable becomes tau. I take a Fourier transform, this is the same, like pull out some 2 pi I squared, as saying tau times u hat plus c squared u hat equals 0, or equivalently, tau minus c squared, there should be a minus sign there. Tau minus c squared times u hat is a function of c and tau is 0. What this is saying is that my function u hat is supported, a Fourier transform of u is supported on this set here. And what is this set? Well, this is just the probability. So functions that satisfy the free Schrodinger equation, at least if they're sufficiently nice, correspond to functions whose Fourier transform is supported on the parabola. Similarly, if you satisfy the wave equation, your Fourier transform is supported on the cone. Satisfy the Helmholtz equation, your Fourier transform is supported on the sphere. So instead of studying solutions to the free Schrodinger equation, we could equivalently study functions whose Fourier transform is supported on the parabola. And in fact, this gives us a way to solve the free Schrodinger equation. So let's take my initial data u naught, which is living in R2, and I'm going to project that function up to the parabola, right? For each point on the parabola, I now have a function on the parabola whose value is the corresponding value of the function u naught. Let's call that function f. And I have a measure d sigma on the parabola, which, given any set here, I project that down to the plane, I just take the weight measure. That's a perfectly good measure on the parabola, that's a perfectly good function on the parabola. And my solution to the free Schrodinger equation is u of xt is f d sigma inverse Fourier transform. So I have my initial data u naught, I lift to a function f on the parabola, I have a perfectly good measure on the parabola, so this is itself a measure on the parabola, I can take its inverse Fourier transform. This is a function supported on R3, that solves the free Schrodinger equation. So a question I can now ask, and then I'll finish, is, well, which p is it true that f d sigma inverse Fourier transform LP of R3 is less than some constant times f and supported on the parabola? LP of the paraboloid d sigma. And in our three, the conjectured range that this is true for p bigger than 3. It's called Stein's Fourier restriction conjecture. And instead of looking at, so to understand this problem, we can instead localize, look at a large ball, radius r, and allow a very big dependence on r. And it turns out that the range of p for which this is true is the same open range for which the original question is true. It's using something called the epsilon removal lemma. And after we've localized to a ball with radius r, then more or less what the picture looks like following. I have a function f which lives on the paraboloid. I have a large ball of radius r. I'm going to cover the paraboloid by little caps. The diameter of this cap is going to be r to the -1/2. And I'm going to consider breaking my function into pieces supported on each one of these caps. And this is a linear operator. So I could write f as a sum of these fi. And then f d sigma inverse Fourier transform is the sum of the fi d sigma inverse Fourier transform. I'm interested in what happens in a large ball of radius r. And I have this sum of functions, each of which is supported on a cap of radius r to the -1/2. Why is that relevant? Well, I could contain a piece of a parabola supported in a cap of radius r to the -1/2 in a little coin of width r to the -1/2 and thickness the square of that, so r to the -1. And when you take the inverse Fourier transform of fi d sigma for an f supported in such a region, you get a function which is more or less constant, at least has well-behaved behavior, on the dual of this convex set. This convex set is a coin. It has thickness r inverse, width r to the -1/2, very thin in one direction, a bit wider in the other. And the dual to that is something which has width length r in a long direction and r to the 1/2 in the other direction. And the direction that this guy points is exactly the normal direction to the parabola at the location of that cap. You might get several copies, but one of the most interesting cases is where for each one of these caps you have exactly one copy. And so the part of my function that was supported here corresponds to this tube. It's foreshortened because it's pointing this way, of length r and thickness r to the 1/2. And this part here corresponds to a tube of length r and thickness r to the 1/2. And so in order to understand the LP boundedness of this operator, what we now have done is we've broken our function up into pieces, each one of which is more or less supported on these tubes. This should look an awful lot like the kind of situation that Hong and I studied. We've now erased it. And so in order, we could ask, how is it possible for this guy to have large LP norm? Well, one way that can happen is if these tubes overlap a lot. That's saying that the supports of these different functions have a lot of overlap. This can cause the LP norm to be large. So this is closely related to the Kakeya conjecture. In some sense, this restriction conjecture is two questions. Given a function, you break it up into what's called wave packets in this way. And we need to understand how the supports of these wave packets interact with each other. The Kakeya conjecture says, because the paraboloid has all these different directions, these tubes point in different directions, there can't be very much compression. So this is a force which causes the LP norm to be small. And then the final step is where these tubes do intersect, the corresponding functions interact with each other. They're not just one, there's some sort of complex oscillation with one. We have to understand the constructive and destructive interference between the functions supported on these tubes. And the conjecture is that there's roughly square root cancellation. So in some sense, this Fourier restriction conjecture, understanding the LP boundedness of this operator, it's two pieces. It's a Kakeya conjecture plus understanding square root cancellation. Okay, thanks, I'll break there.
So actually, I just didn't understand this lifting of the initial condition, U naught up to the parabola. You can explain that.
Great. So there's That's the question of what exactly I'm doing, then there's the question of why it works.
Yeah.
Let's make sure the question of what I'm doing makes sense. So I have a function u naught, which is from R2 to C. And I'm lifting it to a function whose domain is the paraboloid and whose codomain is C. And how am I doing that? Well, at each point on the paraboloid, the value of this function at that point is just the value of my original u naught at that point. So that definition is probably not, there are no subtleties there. And you can similarly define a measure on the paraboloid in this way. And then it is a computation, at least if your function, if your initial data is sufficiently well behaved, let's say smooth, compactly supported, that this procedure where you begin with your initial data, you lift the paraboloid, you have this measured d sigma, you take the inverse Fourier transform, that is solving the sorry, I missed one step. I take my initial data, critically, I take its Fourier transform. Maybe this answers your question.
Okay.
Take its Fourier transform, lift it, undo the Fourier transform.
Right, okay.
Sorry. Yes, that's important. The question remains, what is the LP mapping properties of this extension operator? Yeah, okay. Thank you. That's an important observation. Yeah. Does that answer your question?
It does, yes, thank you.
Great. Thank you for pointing that out.
The question about the LP boundness of Fourier multipliers. So what happens for, let's say, a cone or something where the dimension of the normal set is positive but not zero?
So we're in R3 now?
Let's say, yeah.
Okay.
But we don't have a ball where you have it in all directions, but just a cone where it comes.
Yeah, great. So when you say a cone, we're talking about a solid cone, is that right?
Yes, it's or a union.
What's that? Yeah, great. So this initial statement I wrote down, which says that if this were to be bounded in LP for some value of P, then you have this vector valued analog where you can look at Hilbert transforms in all of the normal directions, and that vector valued analog would be bounded in LP with the same operator with the same range of P. And now the question is, can you construct a counterexample? And more or less the only way we know how to do it is using Besicovitch compression. And so you could say, if I restrict to only those directions in a cone, can I still create Besicovitch compression? And I believe the answer will still be yes. And the counterexample, I'll have to think about this a bit more, but I think the counterexample I want to make is I want to take my original collection of rectangles of dimensions 1 times delta in the plane. I'm going to lift these to be slabs of dimensions 1 times delta. And the say I want them to all overlap in this rather catastrophically bad way. And that was my original set T. How do you make T tilde? Well, instead of just shifting them by distance 1 in their direction, I'm going to shift them by distance 1 in the normal direction of the cone. And this is pulling them all apart. And then I think you're going to get exactly the same pattern. It is a slightly subtle question. If you give me some arbitrary set of vectors, can you construct Besicovitch compression for that set of vectors? Or equivalently, if you have a finite set of vectors, what is the best bound C so that that vector value statement involves Hilbert transform below them? So if these are vectors pointing uniformly if you have n vectors in 1 over n separated directions, then the globe is log of 1 over n plane. But they could point in, say, lacunary directions, and then that's bounded. There's many options. So there's some subtle questions there.
Thank you.
Other questions?
If you kind of a curved space version would be instead of straight lines, you have some tubes around geophysics. I guess as the size goes to 0, it becomes perfectly flat, so it doesn't matter so much. Maybe at some scale it may matter, depending what kind of curvature you have.
There are multiple questions you can ask in a curved setting, some of which, as you suggested, turn into the question of straight lines, but some of them do not. So as one representative example, the sense of what's going on, there's a few different directions people have gone. But maybe one of the more interesting ones is this f d sigma inverse Fourier transform. I could write it a little bit more explicitly if I wanted, like we're a very closely related operator. I'm going to integrate over R2 f of, let's say, x1, x2. This I'm going to call this e sub f omega. This is a point in R3, which has dimensions omega 1, omega 2, omega 3. E to the 2 pi I x1 omega 1 plus x2 omega 2 plus norm of x squared omega 3 dx. And this is, I'm just writing out explicitly what happens when you have a function, let's say in the plane, you lift it, maybe I shouldn't have called it f, maybe I should call it g, doesn't really matter. But if you have a function g in the plane, and you lift it to the paraboloid, and then you take the inverse Fourier transform of that, and you want to write that out explicitly, it would be this, right? I mean, here I'm encoding the paraboloid of a function of two variables, I'm lifting it to the paraboloid, I'm encoding the paraboloid in this complex exponential here. And so that's just the original question I asked. And when you try to perform this, what's called a wave packet decomposition, you get these tubes, which are straight lines, and there's underlying mechanical. This is an example of a class of oscillatory integral operators, which are called Hormander type oscillatory integral operators. And there's other operators in this class, and it was originally thought, I believe, that every operator in this class would have the same kind of LP boundedness as conjecture for the geometry. But that turned out to be false. So we're game, well, the counterexample of a different phase function for which, so this Hormander type operators are phrased in a slightly different language. So it's a slight lie to say they're of this form, but closely related operator, for which the range of P for which these are bounded, LP is not the same. And the reason is that when you apply this sort of wave packet decomposition, the wave packets you get are no longer straight lines, but instead curves coming from a particular family of curves. And you can get a very large amount of Besicovitch compression for this particular family of curves, because you can have a doubly ruled surface. The surface is doubly ruled by curves. Actually, not doubly ruled, but infinitely ruled by curves from this family. So these curves all pack into a surface, and that
looks like a hyperboloid.
Well, okay, so a hyperboloid, or a regulus, if you will, only has two rulings of
Yeah,
right?
okay.
So, but you could imagine an infinitely ruled surface. You can already begin to see this in for lines in 4 and higher dimensions. The surface AD minus BC equals 1, the quadratic type of surface in R4, infinitely many lines to each point. Well, a sphere in R3 has infinitely many circles to each point. So the underlying geometry of the wave packet decomposition is more general type of operator. The wave packets could cluster very tightly into the neighborhood of a surface. And so this is what we call a very strong amount of Besicovitch compression. And this led to a counterexample to a reasonable sounding conjecture about the LB boundedness of the underlying operator. So you asked about the curve setting. So that's one answer to the question. Another answer, so instead of considering Kakeya sets, there's something closely related to these, where instead of having a line in each direction, for each point you have a line passing through that point, where a large subset of your line is contained in the set. And so these are closely related to Kakeya sets. They're called Nikodym sets. You can ask natural questions about those. And in that setting, you can replace line by geodesic. Question makes sense. And sometimes the answer. So there's a paper of Sog and Minicosi from 95, where if you're working in a somewhat different Riemannian manifold, it's no longer a question about dimension, it's a question about something called the Nikodym maximum operator that can have different behaviors.
If not, the point I think you owe to the reception, let us thank again Jeff Zahl.